So Artemis mission has left the lunar influence at this point in time. About 8:35 is when they were no longer being pulled in or kept in the moon's orbit. So that's pretty cool. Cool. They'll be back soon. Let's look at 5.7. So this is number 11 from homework 5.7. White background or black background? Okay. Well, if anybody prefers a light one, why? Out of curiosity. I don't care, but like, it's not going to change. I'm just curious. I do care why your opinion is that way or what your opinion is. How come people don't like the black? Sean, you said white, right? Okay, well, that's a reasonable explanation. Okay, let's check it out. We are 5.7, and this is number 11, and we were asked, okay, we just went through this whole thing. Here we go. Cooking with gas. dy dx, we're told, is some derivative, and we have the wonderful differential equation that says this is e to the x sine of 2y. E to the x sine of 2y. Now, immediately, whether I use it or not, the first thing that comes to my mind is holy double angle. I know that that's 2 sine y cos y if I need it. Now, you might not remember that. Trig cheat sheet stuff. I'm doing trig and pre-calc currently, so of course it's all fresh in my head. But you guys do have the reference sheet in your book, I'm pretty sure, with all the trig identities. Trig stuff, it's possible that we have to use it. Possible that we don't have to use it either, though. So here I am, I'm stuck. What do you want to do? JJ, what's up? So we definitely will do that, but I can't do it yet. What sort of first order differential equations were we talking about? There's another word, an S word. That's not profanity. Separable. Can we separate these? I'm going to multiply by dx and divide by sine 2y. So let's do that on our first step. And then JJ, I like your idea. So we have dy over the sine of 2y is now equal to e to the x dx. Okay, the separable part is important. This is what makes these problems quote unquote easy. But the good news is that we're going to see problems today that aren't easy, but we have an easy approach to it. So make of that what you will. I'm stuck though. I don't know. What do you want to do? Okay, somebody confidently murmured under their breath integral. Just for the record, I don't believe that there really is a confident under their breath murmur. You can be confident and over your breath, just for the record. All right, I'll do the right side. You guys can do the left. E to the x plus c. Okay, that was easy. What's the left side? Ooh, this is cosecant of 2y. 1 over sine is cosecant. So I like that idea, Rafa. Cosecant of 2y. Now, we'll see if I really do like this idea or not. We'll have to, time will tell. What's the integral of cosecant? I think it's negative or positive cosecant x cotangent x, but you'll have to check because I'm all goofed up now. So if it's a derivative, it's negative. Is it negative if it's an integral also? People, let me tell you about my best friend. Page number, don't remember it. It's cosecant x cotangent x. Okay. So the integral of this would be almost cosecant 2y cotangent 2y, but there's an issue. JJ, what did you say a minute ago? What would you choose? Bet, bruh. If we do this, if u is 2y, what's du? 2 dx. Can I just say that this is dx then? Okay, so we can essentially do this whole integral in our head with that little bit written. What's the constant multiple that's going to come out? 1/2. So we'll just kick back in. So here we are. We have 1/2. And then what was the integral of cosecant of u? Cosecant u, which we're going to keep at 2y. Cotangent u, which is 2y, equals e to the x plus c. And at this point, unless there's any major issues, and I'm just trusting you because I was not in integral mode. I mean, I'm trying to be. As long as we're confident that that's the correct integral. Do we have a general solution at this point? For sure. We do not have to solve this for y. I don't want to solve it for y unless, nope, I'm not even going to offer. Let's not solve this for y. Let's not do that. Cool. Is all we're asked to do is find the general solution? Hey, why'd you say 7? Oh, you were talking about number 7. I thought you were saying the answer was 7. Now, I do have a little mistake. Do we have a mistake? We did 11, right? Okay. The answer in the book is very different. Does that mean we're wrong? No, it just means we had a different approach. For this, if you got this answer and you're comfortable with it, can you just give me yes, no, somewhere in there? Straight down if it's not at all. Okay. This is not the only choice, making this change. There's another option that we can take with it. Any other suggestions for what we could have done if we wanted to integrate that a different way? And Abigail, I think you have a suggestion based on the O you just said. Couldn't we pick u to be 2y again? So we're going to have a 1/2 that comes out. And then it'd be the natural log of sine 2y, right? And then we could expand this out a different way. Your book does it that way to get their solution, but the general solution that we have will suffice. Do we need to do it the other way? Okay, if you want, like, just in case, we have 1/2, I'm just going to take it out, the integral of du over sine u. And that's still equal to e to the x plus c, because that side's easy. So all I've done is I picked u to be 2y, the 1/2 comes out, and then now we get this lovely natural log showing up, which is a decent, like, it works fine. 1/2, what's the integral of this? The natural log of the sine of 2y equals e to the x plus c. And then from this point, we have a different general solution. Could we just keep going yak if we wanted? And by that, I mean, that's a weird phrase, so you guys probably have no idea how to answer that. It's an old baseball term. Going yak or yard is like hitting a home run. Cool. We're clearly all had the same upbringing. Sine of 2y, and this is just something that we could do. I know it's 2 sine y cos y. And this is via that old double angle formula. We could change this again some more and keep playing around with it. There's a lot of different options that we can take. This is the more natural one to me. I know that it disagrees with what the book claims. They don't really disagree. They're just written differently. Cool, cool. All right. Hard, easy. Where did you guys waver with this one? The cosecant part? You made the change to cosecant?
No, I just did the...
Your answer is more like this?
Yeah.
Okay. And I'm fine with that. Cool. All right. Well, others? Do you guys honestly check all your odds? Start doing it so that we don't have to spend as much time here so that we know which ones we need to work. But let's check out a few more. Okay, that was number 11. We should probably just check all of our answers, I suppose, if not everybody does that. What should everybody do? Indeed. Okay, 4, 5. These are going to be awful. So I'm going to get the document camera up. Boom. All right, we started at 5. Did you guys get that 4, 5? If you went a step further and tried to solve it for y, kudos to you. Don't have to. We're just looking for an equation that we could plug in an x and a y. You can also look at 6 if you want, but we didn't do that one. Just so you know, you're free to do that.
I was like looking at 5, but I was like looking at 6.
That would make sense. 7. Natural log of the absolute value of y. I'm just going to say abs y for absolute value of y moving forward. Natural log of abs y is 2/3 x to the 3/2 plus c. On number 9, e to the negative y is negative 1/2 x squared plus c. For number 11, what they did that I didn't dive into is if there's a double angle for sine, I would wager there's a double angle for cosecant, and that's exactly what they've done here. Like, they just get a different form of it. 13, e to the y is 5/2 e to the 2x plus c. 15 is an arctangent. It must have been something plus x squared in the denominator. 17 is 1/16 x to the 4th. I'm trying to figure out how far we go. Why? Oh, I was going to say, why didn't we check the homework yesterday? But, right. 19, e to the various forms of this. I hate their fractions. E to the 2x root x over 3. Other forms of that answer that you may have. You might have 2x to the 3 halves over 3. You guys are hard to read today. I was trying to read you 18, which was not the problem that we did, so disregard that in hindsight. 19. Y abs y minus 1 is abs x minus 1. Okay. 21. Sine of y is 1/2 x squared minus 2. Or if you're feeling crazy, y is the arc sine of 1/2 x squared minus 2. Were you feeling crazy? No? Okay. 23. Y squared is 8e to the x minus 4. Feeling pretty good? Okay. Do we do any more past 23? A couple AP? AP 1? 2. 2 to 6. Well, I was clearly goofed up on these. Maybe not. Number 2. Let's take a look. These ones. Feel okay? Do we need, which ones should we talk about with AP problems? Okay, Rafa, what'd you get on 2?
I guess.
On 2C, can somebody second that? I appreciate that. Let's see here. Somebody who doesn't agree with it. Other options? A. It is A. Now, what's the only difference? The plus or minus. If we have 0, 1 on the graph, if I plug in 0, I would have 0, 1 and 0, -1 on this graph. Is that a function anymore? And not that we need a function necessarily, but there's only one value when y is, or when x is 0, and it's 1. Is that going to happen at the positive version of this or the negative version? There it is. And that's you're close if you got C. Okay, on 3. Leanne Marr, what'd you come up with? Bravo. I agree. Number 4, Fern.
Oh, I didn't get that far.
Okay, number 4, somebody who got that far. Delta. I would agree. Number 5. C, let me double check. I'm lost my spot. 5 is C. I'm cool with that. And last but not least, 6. That looks like an arctan to me. Good news, because they all have arctan in them, turns out. What'd you guys come up with on 6? Anybody who did it? Delta. Cool. All right. Am I collecting this or am I adding to this? Add? Okay, cool. If you didn't do 2 through 6, the good news is you now have time to do 2 through 6. Miss Sweet might have already come around and checked it. So I will add problems to it tonight. If you didn't get full marks on it right now, tomorrow I will physically take it. And if you have it finished, it'll represent that. Cool. All right. That is a pretty good zoom in of a pencil. Huh. All right. Today's stuff, much easier. Remember that we are talking about separable first order differential equations, and that's a mouthful. The nice thing about them is every single differential equation that we have had, just you cross multiply or divide, they're easy to separate. Do you think that's true for every differential equation? Probably not. Now, as a quick example, we're going to look at some stuff. Today, our main focus is on solving differential equations that we can't separate and solve nicely. So we have to approximate some stuff. And the cool thing is that this will come in the flavor of what we will lovingly know as slope fields. Okay. Now, as we're dealing with differential equations, there are whole departments in pretty much every university where you will find people whose specialty in mathematics is differential equation stuff. when you look at all the big work that's been done in physics, like if you're totally going physics nerd and you're looking at Maxwell or Einstein and stuff, all of those equations arise from differential equations that they have solved. Like this is the closest that we've been to the language of the universe. Like this is really it. Now, as we're looking at these slope fields, we are going to define them informally and formally here today, but we're just going to say that all that these are at their most basic, is a way to graph general solutions of differential equations. And I'm going to shorthand differential equations with diff-EQ. Okay. Now, when we are thinking about these, the language matters. And like obviously language and math matters when we talk about it anyway. But the general solution part, I really want to zoom in on. What does the general solution of a differential equation look like? I'm going to call on somebody in just a second. You don't have to give me like a concrete example. Just if I have dy dx equals something, and I'm just going to make something up here. You don't have to write this one down. I'm just thinking. When we solve this differential equation, how do we know we're solved? So it doesn't have to quite get to slope intercept, but we could get there. All we really need is an equation in terms, like, theoretically that we could solve for y. Maybe in slope intercept, but it might not be. But we just want equation, right? We need a y equals, or the ability to maybe get to y equals is what we're after. Undo the derivative. So when we're looking at these, if we don't have an initial condition given, and I don't really care if it's this particular derivative necessarily, this would be what? X squared over 2, and I'm just going to do this real quick. X squared over 2 equals y squared over 2 plus c. This is the solution, the general solution of this differential equation. What does the plus c tell me? Like, what's the point of that plus c? Constant. How many c values could you possibly choose? Infinitely many. So if I were to graph just this, how many graphs would show up? Infinitely many. Now, this is not a hard differential equation, but if it were, and I had at least what the graphs look like, and I knew the initial condition, theoretically, we could just put that point and follow. If I can see all the solutions, we could probably pick out the one that's close to it and get our answer. And we're going to do exactly that today. So, turns out, for other purposes, and I guess for now at least, this is how we solve, and I'm going to put some quotations around something because this is only for us, unsolvable differential equations. Now, solve might be a little bit generous of a word here. Approximate would be the better choice, but we are just looking for a function to help us predict based on some changes that we've observed. That's called the derivative. And we'll do a real world application problem of this as well. Okay. Does it seem like this is going to be easier than the stuff that we were doing? My guess is no. My gut says no, but other people are saying yes. The fact that we're solving unsolvable problems makes it seem daunting. Don't be daunted. That doesn't feel right. I don't know. All right, let's do one. So we'll just check one out. If we are looking at this, we're going to do one example together, and then you guys are going to be up at the boards doing a few different things. So for our first example, and I lied, you guys might go up to the board and do these ones too, but we're going to talk about it first. Let's say that we'll do a couple of these. We're going to sketch the slope field. And we'll do a couple of them, but we'll at least talk out the strategy to begin with. Okay, let's say that we had a differential equation that we're going to do one that we can solve, just so you know first. But let's just see kind of the general approach. If I had this, dy dx equals, let's say it's x squared over y. First and foremost, could we solve this differential equation? Is this separable? I multiply by y, I multiply by dx, and it is not terrible. Okay, we could certainly solve this. Now, pretend that we had no idea how to solve it. That's where we need to jump in here. We're just starting with an easy one. What I want us to do is generate a slope field. So we're going to say at, and this is going to be a little bit ugly notationally, unless you want to write all these different points down. We're going to do 1, -3, all the way up through 1, 3. And then we're going to do 0, negative 3. And I know that this is super ugly right now, all the way up to 0, positive 3. And we're going to do negative 1, negative 3, all the way up through negative 1, 3. Okay. I haven't even really shown you or talked about what slope fields are, but we're going to build them together, and you guys are going to help me do something. This equation that I have right now, and we'll redefine this and get this in there, but I'm going to write something here. This give me an equation. Like, this is an equation for dy dx, right? Now, normally if I said this is just an equation in x, we would use f of x. Would you agree with that? So if I just said that instead, and I'm just going to do pink for think over here, if we had y equals 2x, do you guys ever remember changing that to f of x equals 2x? My guess is yes, because everybody's done this multiple times. This should not be a surprise to anybody. Could I do the same thing here and call this f of something, you think? Good. Yes, no questions need to be stopped by me. What do you want me to write the variables of this? What variables are we working with for this function? X and y, right? Okay. Do you agree that this is just a different way to write this? Like, that's really what it is. This is an equation in x's and y's. It's ugly. I don't know which one's uglier. I like this one more than I like this one, but they're the same thing. We can think of it this way. Which means if I want to know the value of this, I need to have an x and a y. So here's what I want you guys to help me calculate out. I want you guys to evaluate, and this is going to switch to green just because we're actually doing it. I want to evaluate f of x and y, which is our differential equation that we have right here, at each point. Now, you will not have to write out as much as I'm going to make you do this here, but I really want to make sure that we can appreciate the work that goes into solving unsolvable problems. Okay, or approximating the answers anyway. So we're going to make a little table. We are going to have x's going this way. We're going to have y's going this way. So we have a wonderful table here. And let's start building it. I'm only going to do like 2 points with you, and I'm going to make you groups finish them. And I would encourage divvy up the labor, but I'll let you guys figure that part out. Are there any coordinate pairs that we are asked to sketch the slope field at? So, Mickey, question. This is a y and a down arrow. That's fair. So I'm just going to have x's and y's. And there's lots of ways to organize this. I just want to make sure we all use the same way. Based on these ordered pairs, what's the smallest x I'm ever going to pick? Nothing smaller than 0 anywhere up here for the x's? Negative 1. So negative 1 is one of my x values. And then all my y values are just going to run from negative 3 to 3, right? So do you want to, let's start at negatives, negative 3. And we'll just do this very first one together. My equation, my differential equation, gives me the value of the derivative, right? And remind me, and there's a whole bunch of answers. What's a derivative? I like that one. Somebody said it louder, prouder. It's just a slope. It's the slope of a tangent line, but they're just slopes. Do you agree then that if I say this differential equation, or the equation of this derivative, just gives me a bunch of slopes? Okay. That's all it's doing. At the point, negative 1, negative 3. What do we get if we plug it in here? What's negative 1 squared? 1 over negative 3. Negative 1/3. Do we need to do one more together before I ask you guys to find all 12 points? There might only be 9. Cool with that? Okay, group it up, board it up, finish this table. You can take your notebooks with you if you want, but I want you guys to calculate it out because we're going to be graphing up on the boards as well. Cool, groups of 3. I can pick them or you can pick them. You get 15 seconds before I pick them. Vamos. Find a marker, find a board. When I have my calculator like this, we use y when we just have a function in x, right? But if we have a function in x and y, then we can't just name it y equals. So z is the next natural choice. It is super important that once you do this on your calculator, you turn it back off here in a moment. Okay, on your mode button, when we open it up, and on the graphing setting. So I hit mode, top left, underneath alpha, and then I see graphing. And on graph, you can either hit enter or you can just go to the right, but this is set on function for you right now. If we go to 3D, it will give us the option to choose Z, so I can do X and Y. This can also graph 3D stuff, just so you know, but I need 3D selected. I hit enter, and it takes me back to my home screen, theoretically. So again, I hit the mode button, I go to graph, and I just make sure it's on 3D. So I just hit to the right once it's there, and I select 3D, I hit enter, So you don't have to worry about the define thing. That was just my typing stuff a second ago. Do we all have 3D setting on? So now when we go to y equals, we should all have Z1. And then let's just check. We had x squared over y. Okay, let's try this. And I'm learning with you guys right now, just so you know. And I just had it, and then I lost it. X squared divided by y. All right, I'm going to get rid of that x. I now have that function typed in, which is exactly what we were just dealing with, right? X squared over y. Okay, moment of truth here to see if this really works. When I go to the table, what I'm really hoping is I see z, x, and y, all three values. Table is not available in 3D mode. That is super lame. We're going to try something else. Okay, if it won't make my table, I'll just tell it what to do. That was Z1, right? Okay, so this is going to be tedious, but let's see if this works. You guys all started seemingly at the same spot. I'm going to try -1, comma, and maybe this isn't a time saver in hindsight, but we'll see. Bless you. -1, -3 is where we started? Is it going to do it when I hit enter? I have no idea.
Yes.
Oh, thank goodness. And then we just need to do this. I can't believe it won't make the table. -2, right? Not -2. That's going to be the wrong thing. Can I generate and maybe save time here? I don't know if I'm really going to save time, to be honest, but we can check all your values. -1. Are these looking like the table values that you had?
Yes.
I can't believe it wouldn't make us a table. That is so disappointing for me. But because it doesn't understand that we have x and y if it's not in 3 dimensions.
Try to look at the graph for it.
Sure. Say that again, K-Rad. No, you can. Like, I'm not reprimanding you. Don't know what that's doing. Hey, there's our graph. And we can rotate it. There's our lovely 3-dimensional graph that if we tilt it in the right area, I think it'll just look like a 2-dimensional graph if we're careful. Yeah, this is what we just typed in. So it exists in 3-dimensional space. Just so you guys can see, it's hard to pick out here because it's 3-dimension, it's not in color and stuff. But can you guys tell, like, we're tilted? These are just our parabolas that we get from our x squareds. Like, I can see the parabola showing up. It's like a cross section near me. And then it's just almost like a saddle. Okay, it does do some fancy graphing stuff. We will get into more of this, but I was hoping we could use it to make our table here. Help me out here real quick. One thing that I do know that is if x is 0, what's the slope? It's 0, right? So I'm going to space out my table. So I know it's 0 here, it's 0 here, -2, -1, 0. So many values, 1 and 2. Okay, so I probably shouldn't have shown you guys that and then said, hey, now pay attention to me. You get 60 seconds to play with your calculator. Go, play around with it, type in different stuff. We'll meet. Is any of the math that we did to make this table awful? Do we really need, like, do you guys think that on the spot you could plug in x and a y and calculate it without making a big table? Okay, I agree. But let's go ahead and look at what this is really telling us. And I really want to stress, every problem will not take this long. I just want to make sure conceptually we see what's happening. Okay, we are going to use all of this to make our slope field. We haven't even made the slope field yet. We've just done all the work to get to it. All we're going to do is we're going to make a coordinate plane here. And I'm not going to label it super hardcore. I'm not going to put dashes on this graph right now. And you'll see why here in a minute. I would encourage, if you have a different color than just black to use, now would be a good time to break out those additional colors. Okay, Instead of putting dashes and stuff, I'm just going to put points. What do you think this point is? 1, 1, and 2, 1, and 3, 1, and 1, 2, and 2, 2, and 3, 2, and 1, negative 1. And I'm just putting all those points that we just did. Now, I'm not doing it super precise, but I am going to make sure that we get every single ordered pair, and we can put dots on the axes and stuff as well if you'd like. When you guys do this on AP tests and things, just so you know, it will not be 16 or 18 points. It'll be like 9-ish, and they'll give you this graph. But I want to make sure that we can see what's happening. All right. So I got all those. In hindsight, did I really need all those? What did I just burn a ton of time doing? Unnecessarily. What's this X value here, do you think? And this one? How far do my X's go? What am I doing? Why'd I go all the way to 3? I'm trying to go to 3, 3. We don't have that many. Do you guys understand the issue that I identified? I don't need all of this. I can keep it. I'm not going to. You can keep it. I only need to go how far in the X direction? Oh my gosh. Sorry, guys. That's my bad. 1. So here's 1, 1, 1, 2, and 1, 3. Everybody okay with that? And you can keep all the others. Here's 1, 0, and 1, negative 1, and 1, negative 2, and 1, negative 3. And then, unfortunately for you, but fortunately for me, I can do this. So I'm going to let you guys draw your dots here real quick. And I'm going to draw my dots here real quick too. Should have gotten some dot paper for this. Okay. I'm going to give you guys a second to get this. I'm not joking. Now would be a great time. But obviously not a joke. It's not funny. But I would encourage colored pencils for this part. If you want some, or a pen, or some, I got a ton of them. It's going to be hard to tell if you don't change color. Not required, but let's check it out. Goodness gracious, this chair is just getting squirrely today. All right, what are all these? And do you guys need a little bit more time to draw it before I start talking? Okay. While you're drawing it, I'm gonna come back. How much money you got? Okay. All right. So, while will you make sure the door's closed, Kalisha? Like, I think there's a wood stop in there. We have 30. What are all of these? These were all slopes, right? Now, we happen to have a graph here. Now, did we ever find the equation y equals something? Like, did we solve the differential equation? No. But does it look to you that we're about to graph all the answers? Probably not super. Check this out. Let's do graph this. All of these are slopes. Okay. You guys have seen windy.com. I can pull it up if you're not familiar with Windy to see where this comes from. How do I know? And I lied. I'm going to pull it up because it's worth talking about. 0. Do you guys agree? Here's a slope of 0 when x is 0. And I'm literally just going and I'm putting in the slopes that we got here. And I will meet back up with you guys in just a second. Please, did you notice anything?
They all move.
Did you notice before I asked?
I did notice Makisha at the line.
Okay, all right. I was purely curious. Okay, now for these, there's a bit of estimate that needs done. It probably doesn't really feel like windy.com here yet, but it's going to start. We've knocked out this whole column. Now, some of it we have to estimate, and I don't care how we do it, but let's pick a point. At 1, negative 3, what was our slope? Negative 1/3. Now, I have the benefit of doing something that says up 1, left 3. So I'd have to go to here. So I know that my slope, if I were to do it, it'd be about like this. Do you guys agree? At 1, negative 3, the slope is negative 1/3. And I just went up 1 and left 3 to get my slope. But I don't need this whole big bar. Now, you don't have the ability to undo it. But does that kind of look like a slope of negative 1/3? What slope would I put here? Negative 1/2. So it should be more steep or less steep? A little less steep at 1/2 than 1/3. What's bigger, 1/2 or 1/3? So which one should be steeper? Negative 1/2 is a little bit steeper, isn't it? Like it must be a little bit steeper. Not a ton, but a little bit. And that's about a slope of negative 1/2. And you're welcome to move back if it's stressing you out, just so you know. What about here? So the slope is what here? Thank you guys for playing along with that, by the way. At 1, negative 1, what is our slope? Negative 1. Now notice, because I have like the scale drawn out, I can draw a slope of 1, negative 1 pretty good. Now, is this perfect for all of these? Like, I'm not getting them perfect, but they're kind of close. Now, could we do this for every single part? Like, here's a slope of 1, and then here's a slope of 1/2, and then here's a slope of 1/3. I'm just putting these slopes here. Now, here's where I think you guys are going to hate me, but I hope in the end you'll appreciate this part. I'm going to pretend like we don't have these tables written everywhere, and I just want to show you something. This table is really helpful if we need to organize our thoughts, but let's pretend I didn't do this. Here's the point, negative 1, negative 3. And if I know my function, and I'm going to write it one more time so I can see it, it's x squared over y. Can we plug in a negative 1 for x and a negative 3 for y right here? So negative 1 squared is 1 over negative 3 is negative 1/3. Cool. Can I draw a slope of negative 1/3 here? Oops, and I'm going to undo it so I can get it. That looks like a slope of negative 1/3 to me. What about if I plug in a negative 1 and a 2 for y? Or sorry, negative 2, my bad. Negative 1/2, so there it is. It's a little bit steeper. And then we get a negative 1 squared over negative 1 is negative 1. And I can see these graphs, or these little slopes. Are you guys still in agreement? Okay, do I need to talk out the last couple, or can we just draw them? Okay, slope of 1, slope of 1/2, slope of 1/3. Now, we do not have a crazy big slope field right now. I'm going to show you a crazy big one. We used like, what, a bunch of points, 18-ish. Check it out. That slope field that we have there is okay. I'm going to get up a big one. Not that. GeoGebra slope field. And we're going to look at the real slope field for this. Okay, so I'm going to let this load and change the function. This is a different function. Notice they used y prime. I'm going to use dy dx while we write these. But it was x squared over y. And then let's see, we went from negative 1 to 1. And we went from negative 3 to 3. Okay, as we look at these, and I don't like that step size, so we're going to make this step 1. That didn't change it. We're just going to change the scale. That's fine. 10 and negative 10. I'm fine with that. Okay, if we look at this lovely slope field, and let's see if it lets me join in or zoom in. Oh my gosh. Let me do it. Don't freeze. Oh my God. Gosh, sorry. All right. I have something typed in funny, and I'm trying to figure out why. That would explain it. Okay. So we're just going to make it huge. Okay. And we're going to get rid of that one. If we look, and I wish I could zoom in here, does this kind of look like what we just drew? Now, if we look at this one, and these, get out of here, Ed. Sorry, I don't know how to get rid of it without opening it. I'm just going to copy and paste a little part of this and drop it in so we can compare. What? Okay. Does this kind of look like what we just did? There's ours. Here's theirs. But I just want to check. At 0, are all the slopes 0? And then at, it's not going to let us do it. Is it a little bit steeper here in a positive direction? Is it a little bit lower here in a negative direction? We see the same thing. Now, with more points, it's easier. When we get a particular solution, if I give you an initial point, we can find the general or the actual solution, right? Now, even if we can't solve it, hypothetically, let's say that I knew that this point was on my graph. And we'll pick up here tomorrow. I'm going to keep you guys like 20 extra seconds. If I know that this is the slopes of the function, what way do you think it had a slope of 0 here, right? And then what's it start doing? The slope starts getting bigger, and it looks like it's probably eventually going to wind up here. Over here, the slope, it follows down. It gets really steep, undefined for a second. And then it looks like if I just follow it back through, does it look like I'm following that path? Now, I just want to show you, I did solve this, just so you know. I didn't leave the thing around. We will jump in right here tomorrow. Cool.